So as long as my frequencies are low enough, I'm okay. But what if they're not low enough? What happens? Well, now, let's suppose I have a higher frequency thing. So this is some random function, and it has some high frequency. So here's its f of u, and you see its w goes out a little bit further. If now I multiply that by the same comb of m, I'm going to convolve this thing with that 1 over m comb that I had before, and I'm going to get this part here. Now remember, these things actually sum. I'm drawing each individual component, but in reality, this thing would sum and come back up here, right? So these things would sum and come back up there. And this area right here is where this essentially, this energy has folded back on itself. It's overlapped, and then they're going to add, okay? That high frequency that was really this little edge thing here, okay, or you think of it there, is pretending it's low frequency. That's the aliasing. And once you've aliased the signal, once you've done this operation, you cannot undo it. The high frequencies have pretended that they're low frequencies, and you can't separate them out from real low frequencies. You have to remove the high frequencies before you do the sampling in order to remove the aliasing. So how might you do that? Okay? Well, how do you remove high frequencies? Well, we know how to do that. We convolve with H, maybe it's another Gaussian. What does that do? That reduces the high frequencies. So the frequency spectrum of the convolution of f and h has much less high frequency. So that H is what's referred to as an anti-aliasing filter, and it has the net effect of trimming the high frequencies of the original signal. So that then when I do the multiplication by the comb, which is shown here, right, I'm now convolving that with a comb filter in the frequency domain, but I don't get that overlap, right? So no aliasing goes on, all right? And then to recover the signal, whatever I get after I reconstruct from that using the new sampled convolved function, I can throw away any high frequencies because those are not real. That is, so just the way we did with the CD, right? We low pass filtered the microphone, did a to D conversion to get some digital samples. We did a D to A conversion to get an analog, and we knew that any high frequency that showed up, that's not real. Okay, we could low pass that away and recover the original signal. So that's summarized here in terms of aliasing. When I don't have an anti-aliasing filter, I get these overlap regions that cause me to get aliasings that I cannot remove once I've done it. But with an anti-aliasing filter, I don't get that overlap. So that's the mathematics behind aliasing.